What's up, geometry students? We're here to talk about some probability stuff again today, and I want to get into the idea of what it means to be conditional probability today. And so that means we're not looking at things that are completely unrelated. We're looking at things that have to do with some other condition happening. And so first I want to start with kind of the formula that goes along with this, and what the notation is for it. So we have this probability of B and then this vertical line A. The way we read that vertical line is the word given. So this says probability of B given A. So the probability that event B occurs, given that event A already occurred, is probability of B given A. And the way we figure this out, the probability of B given A would be the probability of A and B. Remember, that's our little symbol for and. Probability of A and B divided by the probability of A. And I think this isn't a bad thing to know, but I think when we look at a few examples of this seems kind of strange right now, but it'll make sense why this is the case once we look at an example or two of this. So we're going to do an example with cards again. Remember, if you're not real familiar with cards, look at that card reference sheet I put on Google Classroom for you that talks about all the different things that happen in a deck of cards. It's going to be helpful. So you draw a card from a standard deck. Remember, standard deck, 52 cards. Event A is you draw a 7 from that deck of cards. Event B is you draw a diamond from that deck of cards. Event C is you draw a red card from that deck of cards. So we're going to see if we can find some probabilities if those are A, B, and C. So I have them all in notation here instead of in words. So first one is probability of A. In other words, what's the probability that you draw a 7? Now, in a deck of cards, we've got 4 sevens. And so we've got 4 sevens out of the 52 total cards, which means the probability that you draw a 7 would be 4 out of 52. Or if you wanted to simplify that, which you should, by the way, and I noticed some of you guys, that's the part you were leaving out on a few of the assignments. If you're going to leave your answer as a fraction, remember you're allowed to do a fraction, a decimal, or a percentage. But if you're leaving your answer as a fraction, it needs to be simplified. And so this is 4 out of 52, but should be simplified then to 1 out of 13. So next part, probability of A and B. All right, so let's look what A and B are again. Probability that when you draw one card from a deck, it's both a 7 and a diamond. All right, so we have to think this through. How many cards in a deck of cards are both a 7 and a diamond at the same time? Do you notice the only card that actually satisfies both those is the 7 of diamonds? So that means there's only one card that is a 7 and a diamond. And remember, for and to be a desired outcome means both of those things have to happen. It has to be a 7 and a diamond. And if there's only one card where that happens, then this is only 1 out of 52. And so now what we're going to try to find is probability of B given A. Now I did these two things first on purpose because do you notice those two are part of the formula if I want B given A? And so if I want the probability of B given A, I can really just put these in. Now I'm going to be a little clever about how I do this because I'd like to stick with the same denominator. So even though this is 1/13, I'm going to use the 4 over 52 here. And so probability of A and B is 1 over 52. And so, I'll tell you what, I'm going to do this in a different color at first so we can see when we get to the final answer. So we've got 1 over 52 for A and B. And then that's over top of 4 over 52. Now, this is where we got to remember just a little bit about how we divide fractions. If I have a fraction divided by a fraction, the way to undo that is multiply by the reciprocal. So this is the same thing as 1 over 52. Remember, reciprocal means we flip it over. So dividing by 4 over 52 is the same thing as multiplying by 52 over 4. Now, if you're real good at working with fractions, you know that these 52s could just cancel here. And that's what I'm going to do. And so this leaves our answer being 1/4. All right, now let's think this through a different way. Now, this is perfectly fine. It'll get you the right answer. But I'd like us to be able to logically reason through this as well and not be stuck just blindly plugging numbers into a formula. So probability of B given A. Let's put this in words. What's the probability that you draw a diamond if you know you drew a 7? Given that you drew a 7, so you know you drew a 7. So if you already know you drew a 7, probability of drawing a diamond given that you know you drew a 7, how many 7s are there in a deck? We've got 4, right? Okay, so that means our total possible outcomes is now from 52 down to 4. We're only looking at the 7s. And so we've got 4 7s to choose from. Now, of those 7s, how many are a diamond? Just 1. So what's the probability of drawing a diamond if you already know that you drew a 7? Well, there's 1 7 that's a diamond out of the 4 7s total, so it's 1/4. Right, is that making sense how we're getting that? Now, that doesn't mean this formula doesn't work. It works just fine. It just means you don't have to use it if you can reason through what's happening without it. So here, let's try another one. Probability of A given B. Now, do you notice we've got the same 2 letters here? I wanted to do this on purpose because I wanted to see, does the order matter? B given A, is that the same thing as A given B? Will it come out to the exact same answer of 1/4? Well, let's think about this in words. What's the probability that you draw a 7 given that you drew a diamond? Now, if you know you drew a diamond, you might have to count across to see how many there are, but there's 13 diamonds total in a deck of cards. And so that means we only have 13 cards to choose from. That's our bottom number. We're not looking at all 52. We already know it's given that we drew a diamond. So there's only 13 to pick from. Of those 13 diamonds, how many are a 7? Only 1. And so our probability of A given B is 1 out of 13. Now here's what I want you to notice. It's not the same answer. The order is important when we're doing a given problem. So A given B and B given A are not the same thing. All right, let's try another one. This one's kind of an interesting one. Probability of C given B. All right, we haven't really got C involved much here yet, but C is drawing a red card. And remember, half our deck is red, half our deck is black. So we've got 26 red cards, basically. So what's the probability of drawing a red card given that you drew a diamond? All right, so it's given that you drew a diamond, which means we're not looking at the whole deck of 52 cards anymore. We're only looking at the 13 diamonds. Now, of those 13 diamonds, how many are red? Well, if you notice, every diamond is red. So doesn't that mean all 13 of them are red? So that means we've got 13 out of 13. Or in other words, the probability is just 1. Or in other words, it's guaranteed to happen. If you know you drew a diamond, you had to draw a red card. So the probability of drawing a diamond or drawing a red card given that you drew a diamond is 100%, or 1. Now this one's same 2 letters but different order. We saw a minute ago it's not necessarily the same answer, so let's check this one out. What's the probability of drawing a diamond given that you drew a red card? And so half the deck are red cards. Half of 52 is 26. And so we've got 26 red cards to pick from. Right. Now, of those 26 red cards, how many of them are diamonds? We've got 13 diamonds and 13 hearts. And so 13 of those 26 cards are diamonds. And so we've got 13 out of 26. However, remember, if you're going to leave your answer as a fraction, it needs simplified, and this simplifies quite a lot. 13 is exactly half of 26, and so that would be 1/2 if we simplify that. All right, is that making sense so far, how we're getting all this given information? All right, now enjoy a short break until we come back again. All right, guys, welcome back. So what I want to do next with the conditional probability part is I want to talk about two-way tables. We talked about these a little bit yesterday, and so we kind of have an idea of how they work with all of our information in our rows and columns. And this particular one is actual information from the Titanic. So the boat that sank, a little over 100 years ago. And so we're going to see if we can come up with what happened with all the people who were on that boat and whether they survived or died, depending on where they were in the ship. So we've got first class, second class, third class, and crew members. And then we've got our totals column for survived, died, our totals column for the number in each class, which means our total number of people aboard the ship was 2,201. All right, so let's see if we can figure out a couple probabilities based on this information. So first off, what is the probability of dying and being in second class? Now remember, we've mentioned this a couple times. This is really an operator. That tells us what to do. So the word "and" is extremely important here. That means both of those things have to happen in order for this to be a desirable outcome. And so we want dying and second class both. So looking over here, here's all the people in second class, here's all the people who died, here's the people who died and were in second class, which means 167 people satisfied both of those pieces of dying and being in second class. And so we've got 167 people out of the 2,201 people who were in second class and died. So we're going to figure out what this is as a decimal, because when we start to get into problems like this, it's really hard to simplify the fractions. I don't really want to try to see if 167 over 2,201 can simplify. So I'm going to divide the two out. So 167 over 2,201 is about 0.076, or if you like a percentage, moving the decimal point two places, about a 7.6% chance that a passenger on board was in second class and died. So this actually isn't anything new with conditional with the givens that we're doing today. I just thought it'd be a good chance to review some of the stuff we've done before. This one, again, isn't going to be something new for what we're doing today. But this next one says, what is the probability of being a crew member or surviving? Now remember, or is the operator here. That means if either of these two things happen, then it's a desirable outcome. So crew members. We've got crew members, 885 of them. All right, so we got 885 total crew members out of the 2,201 people. So we got 885 out of 2,201. Now that's just the crew members. And then the survivors, we have another 711. But here's the problem, and we saw this yesterday. If we have or, it means add the probabilities, but it means add the probabilities and subtract any overlap. So if there's anybody who's in both of these groups at the same time, we've got to subtract them out. So do you notice we got 885 crew members, 711 survivors, but of those survivors, 212 were crew members. And so that means these 212 people got counted in the survivors, got counted a second time in the crew members, which means they've all been counted twice. They're only one person, they can't count twice. And so that means I need to subtract them out once since they've been counted twice. So a good way to remember, when we have or, it means add the probabilities, but it means add the probabilities and subtract the overlap. And so putting all this together, we've got 885 and another 711. So 885 plus 711 minus 212. So 885 plus 711 and then minus 212 is 1384. So we've got 1384 over 2201. And that might simplify, that might not, but instead of trying to simplify this horrible fraction, I'm just going to go ahead and divide the two out and get this as a decimal or a percentage. So it's like 0.6288. So I'm going to say it's about 63%. Chance that you're either a crew member or survived. Now, here's where we get into kind of the new stuff we're learning today. The operative word here, do you notice there's no ors or ands in this, but there is this word. Given means we're doing what we were talking about today. So what's the probability of dying given that you were in first class? All right, now remember given changes the total number of possible outcomes, because instead of looking at all 2,201 people, it's given that you were in first class. If it's given that you were in first class, that means we're only looking at first class passengers. And so kind of the rest of this over here becomes useless to us. We're looking at this column and that's it. And so our total number of first class people, because it's given that you're in first class, is 325. So we're not looking at the whole group, we're only looking at the 325 in first class. And it says, what's the probability of dying given that you were in first class? So of those 325 first class passengers, how many died? 122. And so our probability of dying, given that you were a first class passenger, is 122 out of 325. Which again, instead of trying to simplify that, I'm just going to get that as a percentage. And so it's like 0.375, and so I'm going to say it's about 37.5%. So there's a 37.5% chance that you died if you were in first class, given that you were in first class. So then D, what's the probability of dying given that you were in third class? Now, something you might have heard about the Titanic is that they let all the first class people get on the boats first, and they had a much better chance of survival than the people who didn't pay as much to get on the boat, and they ran out of lifeboats, and they just said kind of too bad for those people. Well, these are the actual stats. This is going to tell us the story, really, whether that's the case or whether that's not the case. And so, probability of dying given that you were in third class. Now again, it's given. That's our operative word here. So we're not looking at everyone. We're only looking at people who are in third class. So that's this column right here, which means we've got 706 people total. 706 third class passengers. Now, of those 706 third class passengers, we want the probability that they died. So of these, how many died? So of the 706, 528 died. So there's the probability that you died given that you were in third class. Now again, let's get this as a percentage. And by the way, if we're talking about comparing things, putting them both as percentages just makes it easier to compare because they're both in the same metric and they have the same, like, out of 100 is always what a percentage is instead of out of whatever the fraction simplifies to. So let's do 528 divided by 706. And that tells us the probability of dying if you were in third class was 0.747. So I'm going to say about 74.7% chance of dying if you were in third class. So since these are the stats from the actual Titanic, here's my question. Did it actually matter if you were in first class or third class? Did your chances of survival or chances of dying really matter? Did the class you were in have an impact on your chances of survival? Well, if you were in first class, you had a 37.5% chance of dying. If you were in third class, you had a 74.7% chance of dying. Much higher chance of dying on the Titanic if you were in third class than you were in first class. And I wanted to talk about this example too because this is going to lead us into what we're going to talk about tomorrow, which is what we're going to call independent events. And the opposite of independent events is dependent events. These two events are dependent. The class you're in and your survival were dependent. The class you were in changed the probability of survival. These are dependent events. If we found both of these percentages and they came out to really close to the same thing, we would say that the class you were in did not matter. But here, it definitely made a difference. First class passengers were much more likely to survive, much less likely to die than third class passengers. And so it did make a difference here. Now, I don't want to get into like the morbid statistics because we're in the middle of a crisis right now, really. But do you notice that this thinking is actually really relevant to our COVID-19 situation we're in right now. And let's think about some of the questions that people are asking. What are the chances that you die from COVID-19 given that you're over 65? That's exactly what we're talking about here. What are the chances that you die from COVID-19 given that you're under 19 years old? And does it matter? And the answer is yes, it makes a huge difference. Your chances are much higher if you're over 65 than if you're under 19 years old. And so these are some of the stats that people are using today, and these probabilities are really what people are concerned about in computing with this current crisis that we're in. So I just wanted to give you kind of that tie-in to what we're doing and say that, you know, even though we're talking about something that happened 100 years ago here, this is happening right now, that these statistics and these probabilities are being computed for this current situation that we're in as well. So that'll wrap it up for conditional probabilities. Tomorrow, the big thing that we're going to talk about is dependent and independent events and how to tell the difference between the two. All right, thanks guys.